Hello, everyone. How are you doing? I trust you're all doing great. James from JT Smith Tutoring here. Today, we are actually going to be looking at an example of solving a linear system of two unknowns with one solution. I know of late we've been looking at how to determine the number of solutions. So is it infinitely many solutions? Is it exactly one solution, or is it no solution without us actually working out the system? So this time around, we are actually going to be working out the system to actually verify what we have been saying all this while. All right, let's get going. We have an example here. It's a very simple example just to get started, just to whet our appetite, to set ourselves on a voyage of discovery. So take this gen with me. Solve the following system, which have got two unknowns here, x and y. So we have got x minus y is equal to 1, and we've got 2x plus y is equal to 6. So there are plenty plus ways in which you can actually do this. I've just given you 4 here, but that does not mean that that is the only way to solve this. All right, taking you guys back to high school, you were introduced to solving simultaneous equations by method of substitution, by method of elimination. Okay, beautiful. We'll look at that. Then now that this is your first year at university level and we're introducing you to linear algebra, we are going to be solving most of this stuff not by substitution or elimination as we were used to, but we are going to be introducing matrices. We are going to be talking about row operations there. We're going to be talking about row echelon form, reduced row echelon form. We're going to be talking about Gauss-Jordan versus Gauss elimination and all that kind of thing. But let's get started. Right, by substitution, you can see that from your equation 1 here, you can either have x is equal to y plus 1, or you can have y is equal to x minus 1. All right, I decided to make my y here the subject of the formula, thereby having equation 3, x is equal to y plus 1. Sub in that x is equal to y plus 1, which is my equation 3, into equation 2. So we are literally going to replace wherever we see an x here with y plus 1, which is what you have here. So distribute these two inside, you're going to get 2y plus 2 plus y is equal to 6, okay? 2y plus 2, that's plus y is going to be 6, so which is 3y is going to be 4. Then you solve for your y is 4 over 3. Okay, fine, I'm happy. I've gotten my value for y. So how am I going to get the value for x? It's just a matter of substituting that value for y into any one of these, either into 1 or 2 or 3. I've decided to make my life a whole lot easier and substitute it into equation 3. Okay, boom, there we are. You find out that you're going to have x is equal to 7 over 3. Then we can make our conclusion here. Thus, the system has one solution or a unique solution. X is equal to 7 over 3 and y is equal to 4 over 3. Take note, why are we saying exactly one solution, or why are we saying a unique solution? It is exactly one solution or a unique solution in the sense that x will never be any other value apart from this value which we've calculated here. Y can never be any other value apart from this value which we've calculated here. That's why we call it what? Exactly one solution or a unique solution. All right, let us move on to elimination. All right, now we're going to solve this simultaneous equation by method of what? Of elimination. All right, cool. So what I've decided to do here is to multiply the first equation by a -2, then add equation 2 to it. By so doing, I'm actually eliminating what? X. So minus 2x plus 2x, the x is gone. 2y plus y, I've got my 3y here. Minus 2 plus 6, I've got a 4 here, and I've created again in equation 3, which is exactly something that you have seen somewhere before. So 3y is equals to 4. You solve for that, obviously, you're going to get y is equal to 4 over 3. That was from equation 3. So I'm going to sub that y is equal to 4 over 3 into either equation 1 or equation 2. You have seen this before. So x is going to be 7 over 3. Okay, you conclude again by method of elimination. The system has one solution or a unique solution. X is equal to 7 over 3 or y is equal to 4 over 3. Okay, beautiful. Now I'm moving on to matrices. Okay. So as far as this is concerned, I'm assuming quite a lot of things here. You know what a matrix is. You know what is a coefficient matrix. You know what is an augmented matrix. You know what row echelon form is. You know what reduced row echelon form is. At this point in time, I'm just assuming you are aware of all those concepts that I've just been discussing just now. All right, beautiful. Right. Augmented matrix, guys, if you have your coefficient matrix and you add in the color matrix of your results, then we call it what the augmented matrix. In English, to augment is just to make something bigger by adding something to it. So you started with your coefficient matrix, then you added the color matrix of your results. So this line here, we call it what? The augment. And this is what we've actually replaced the equal sign when we are converting it from standard form to augmented matrix form. All right, beautiful. I want you to see something here. When it comes to row operations, do you notice that this row operation which I have here is exactly what I was doing when I was talking about elimination. I have multiplied my first equation with a -2, then I've added the equation 2 to it. All right, this is exactly what you're doing. So when you are dealing with matrices, each row, it actually represents what? The equation. So when you say multiply row 1 with a -2, and then add it to row 2 to get a new row 2, that's exactly what we're doing here, okay? So we all know what we are going to do here, either Gaussian elimination or Gaussian-Jordan elimination, of which I've decided to solve this by Gaussian-Jordan elimination, whereby I'm actually going to convert this to reduced row echelon form. But you can see from here, you can stop anyway and actually start solving again the system. All right. So I need to have a 1 here, which is my leading one, which is I have it exactly where I want it to be. I want to make this 2 a 0 here. I want to have a 1 here, and I want to have a 0 here. This is exactly what I am doing right here. Okay, beautiful. So I've got my 0 where I want it to be by this row operation. And by this row operation, I'm going to have my 1 where I want it to be. And by this row operation, I'm going to have my 0 where I want it to be. So I have it now in reduced row echelon form. And you can read from there, the corresponding system of equations is actually going to give us what? X is equal to 7/3 and Y is going to be 4/3. There we are done. Okay, beautiful. Another way in which you can actually do this is that you can solve this graphically. I've drawn my 2 graphs here, and you can see that they are actually intersecting at a particular point in this coordinate plane, which is my XY plane here. So you've actually solved the system by graphical one. So you just have to know how to interpret it geometrically, even without you having the graph. So it's a unique solution, or exactly one solution to a linear system of 2 equations is a point in the coordinate plane where the 2 lines are actually going to intersect, right? That is, if these 2 lines are not going to intersect, it's either they are parallel or they are actually coincident lines, they are lying on top of each other, but we'll get to that. Right, so the geometrical interpretation of that is that we have, this is actually representing a point in the coordinate plane where these 2 lines are actually intersecting, and they're intersecting at this particular point. All right, but how do I know whether the solutions that I have, they are correct or not? I have to plug in these 2 values into our original equations and see if they are going to satisfy both equations. Take note, they have to satisfy both equations. Otherwise, if it satisfies one equation and not the other, then it is not a solution to the system. They must satisfy what? Both equations. All right, guys, boom, we are done. Allow me to do what my mama taught me. She would say a good visitor knows when to leave, or she would say a good dancer knows when to leave the dance floor. All right, guys. Adios, amigas and amigos. Till we meet again, I want you to know that here at JTS, we are committed to keeping you mathematically informed. Bye.